Section 1.6 is miscellaneous equations. So far, we have dealt with several types of equations. We dealt with linear equations, and in that section, we dealt a little bit with absolute value equations as well. And then you had some sections on quadratic equations and rational equations. And I think that's kind of where we stopped with the last couple of sections. So this is the sort of all-inclusive, everything that doesn't have its own category kind of thing, with a wonderful title, Miscellaneous Equations. So we're going to hit on about 3 different types of equations in this lesson and how to solve those equations, okay? So our first type of equations we're going to look at are root equations. Now I want you to write in big, bold print right now next to whatever you've got going on this, always check solutions. It's one of those you should do it as a good idea kind of things in general, but for root equations, and in a minute for absolute value equations, it's like you always have to check them. Because sometimes things happen and you get solutions, or at least something that you thought was a solution, and it doesn't work, okay? And it's really common to have that happen in root equations and absolute value equations, which is 2 types we're going to look at today. All right, so with a root equation, your goal when you first see the problem is to make sure that you have not the absolute value, but the root, the radical part, isolated, okay? So this one's like already set up like that. We don't actually have to do anything to make that happen. But if it weren't, that would be our first step. So we want to make sure that the root is by itself and everything else is on the other side. Okay, everybody good with that step? So you got a freebie. It was already done. So then, on the left-hand side now we have a square root of x minus 1. How would we undo a square root? We would square it. Good. So we're going to square both sides of this equation. On the left-hand side, the whole point of undoing or doing an inverse operation is that when we square root and then we square, we end up with what's underneath the radical. That's called the radicand, all by itself left over. So x minus 1. Now on the right-hand side, you must be a little bit careful. Oops, I didn't write my square. You're going to have to multiply x minus 7 by itself, and that's not the same as multiplying x by itself and 7 by itself. You've got a binomial, and you're going to have to FOIL. So your x minus 1 on the left is sort of fine, but on the right-hand side, you're going to have to actually distribute that out. So if I distribute out x minus 7 times x minus 7, what do I have?
X squared minus 14x plus 49.
Very good. X squared minus 14x plus 49, right? Okay, good. Okay, is everybody good with that? That's right? Okay, good. All right, at this point, the problem actually becomes something you did in the last section, and this is 1.5 if I remember right, or maybe it's 1.4. It's the quadratic section. Because you have a quadratic equation, all right? And there's a couple of different ways you can solve a quadratic equation. Well, there's actually quite a few different ways we did in that section. The probably most friendly way is to factor things, right? But you can't just factor things as they are. They have to be factored where you've got a 0 on one side of the equation. So if you're going to attempt to factor to solve, you've got to get equals 0 on one side. And that's a good way to attempt to solve a problem as a first step because it's usually the quickest way. I mean, quadratic equations, completing the square, you can do all of those things, but factoring is usually the fastest. So if we take this equation and we try to get everything moved, I would be tempted to move it to the right-hand side, because then my x squared would stay positive. You guys good with that? So we'll do 2 steps in one because I think you guys are totally capable of handling it. We're going to subtract the x, and we're going to add the 1, all at the same time. And if you can't handle it, well, you can do it in 2 steps. All right, so we have x squared. How many x's then do we have? Yeah, negative 15, right? Negative 15x. And then what's our constant term?
50.
It's 50. Good job. And if, it works out well, what our hope is anyway, is that we're able to factor what's remaining. And if you need to use the AC method, if it were something that were very complicated or that you weren't sure how it factored, AC method's great. On this one, trial and error is not too bad because there's a linear, there's a coefficient of 1 in front of the quadratic term x squared. So that's friendly, because I can put the x and the x here. Now taking a look at the 50 at the end, I want 2 numbers that multiply to give me 50, but they add to give me negative 15. Good, negative 10 and negative 5. And because they're both negative, they will in fact multiply to give me a positive, right? And because they're both negative, they will add to give me a negative. So the signs are correct. It's a good thing to check on those signs because that will trip things up pretty quickly if you just miss one tiny little bit right there. All right, so taking a look at that, what's the next step in solving a quadratic factoring kind of like this? Right, good. So we're going to set them each equal to 0. X minus 10 equals 0. X minus 5 equals 0. So what does x equal? 10 and 5. And I say that they equal it. I mean, our work shows that that's what our solutions appear to be. But these are definitely like proposed solutions. These are sort of suggestions of what might work. Remember, this is a root equation. And one or both of these might actually not work in our original equation. So we're going to go back to our original equation before we squared it. Okay? I'm going to take this piece before we squared it. And we're going to check each of the solutions that we got. I'll check x equal 10 first, just because that's my first one listed. And we're going to check sort of partially in our head, but we're going to write it down a little bit of it. So write down as much as you need to see. So we're putting the number 10 in. So 10 minus 1 is 9, and then the square root of 9 would be 3. So on the left-hand side, I have 3. On the right-hand side, I have 10 minus 7, 3. And that's true, right? It works, okay? So x equals 10 is for real a solution. It's not a proposed solution anymore. It really works. We checked it. It's beautiful. It is beautiful. I agree. All right, so then x equal 5 would be our next proposed solution. So now I have 5 minus 1. That's 4. And then the square root of 4 is 2. So on the left-hand side, it's 2. On the right-hand side, I put in 5, and I have 5 minus 7, and I have negative 2. And that is not true, right? It's false. This does not work. So why did it sort of look like it might work? Well, the reason that that happened was because remember what our very first step was here when we solved this? What do? We squared it. What would happen if we squared both sides of this 2 equal negative 2 equation? You'd get 4 on both sides, and that would be a true statement, right? So the reason that these proposed solutions sometimes happen is because in the squaring process, signs can change. Does that make sense? So that's why we don't have to worry about it all the time, but we do have to worry about it with root equations. All right? Any questions on this one? Oh, so our final answer then, like if you were putting this in my math lab or whatever, would be that x equals 10. You don't have two solutions. This one did not work. And remember, I used the word one time before where it's called extraneous. It's a solution that sort of came about as a possibility, but it didn't end up working. Okay, so we only have one solution, x equal 10. All right, what about this next one makes it look more difficult?
There's 2 radicals.
That'll do it, right? There are 2 radicals. Now, you could deal with the 2 radicals on the same side like they are, or you could move one of them. And either option is fine. You can work with it. I'm kind of a fan of moving one of them. I think it makes it look a little bit cleaner. So that's the way I'm going to proceed with the problem. But it will work out if you leave them as well. So I'm just going to move the square root x one over because it's negative, kind of like positive values myself. So we're going to end up with the square root of x plus 40 on the left, and we will have the 4 plus the square root of x on the right. Okay, so I just added the square root of x on both sides, like this. Okay, everybody good so far? Okay, the process is going to be the same as what I did before. My goal is to eliminate radicals, and I can eliminate the radical on the left by doing what? Squaring it. So we're going to square both sides. Now on the left-hand side, because it's a radical that's then squared, or actually a square root specifically that's then squared, I'm going to cancel those out. Those are inverse operations, and I have x plus 40 left. But on the right-hand side, I have 2 terms separated with addition, right? The square root's only over part of it, so I can't just square each individual piece. That's not true. I have to FOIL, just like I did on the last problem, even though there wasn't a radical that still remained on the right. Okay, so I have to multiply this by itself. So on the left I have x plus 40, that part's fine. On the right, as I distribute and FOIL and multiply this all out, what do I get?
16 plus 8 square root of x plus x.
Very good. So the 16 is 4 times 4, obviously. The 8 square root x comes from the inner and the outer terms. They both match. They're 4 radical x, right? And then when I multiply the last two terms together, square root of x times square root of x, I get x. Now, the unfortunate part, of course, at this point, though it's not unexpected, is there's still a radical in there, okay? So we're still going to have to deal with the radical here in a minute, or do it again kind of a thing. But this is better than it was before. I don't have as much going on. In fact, as I start to simplify, what do you notice happens to the x's? They cancel. I've got x here, and I've got an x here, and if I were to subtract x from both sides, those two would subtract off. They wouldn't be there anymore. So I actually can simplify this pretty quickly to 40 equals 16 plus 8 square root x. Now, just like on the original, first problem over here, my goal at this point is to get the square root of x alone, right? Isolate the radical. What would be my first step to doing that? Subtract a 16. Sounds good. Remember, we're working from our way from the outside in. So moving from the things that are furthest away from x to the things that are right beside x. 40 minus 16 would be? 24. And then I have 8 radical x on the right because the 16 is added to 0. Now what? Divide by 8. Okay, so that's 3. 3 equals the square root of x. Now what? There we go. We're going to square both sides now. So what does x equal? 9. And again, that's a proposed solution, right? I only have one proposed solution here. But it is sort of just a possible solution at this point. We need to check and make sure it worked because we squared twice, right? I mean, so we had 2 possibilities of places where this sort of could have gone all wrong. Okay, so we do need to be very careful. So let's go back up to the original equation and check it out. If I put a 9 in for x, 9 plus 40 would be 49, and the square root of 49 would be 7. So the first piece is 7. Whoops. Sorry, keep hitting the wrong buttons. 7. It was minus. And then I have the square root of 4. I'm sorry, not 4. The square root of 9, which is my number 9, which would be 3. So I have 7 minus 3 on the left. And I've got 4 on the right, and 7 minus 3 is in fact 4. This is true, correct? So at this point, we recognize that the solution of, or the proposed solution of x equal 9 actually works. Now, what would happen if it didn't? What would I answer to the question? I would say no solution. And is that possible? Yeah, it's definitely a possibility. We don't have to have a solution to every single problem. We can have no solution as a legitimate answer. But this one didn't. This one had x equal 9. All right. I have a rational exponent on this one, 2 over 3 equals 1/2. So this is grouped with the other two because it can be changed into an expression that's in radical form. So that's where we're going to start. How would I rewrite this in radical form? Okay, so the 3 on the bottom here is a cube root now of x squared. Is everybody good with that step? Because that is correct. Good job. Yeah. All right, so I didn't do a cube root before. They were square roots. And I undid a square root by squaring. So how will I undo a cube root? By cubing, right. So we're going to cube both sides. On the left, I will be left with an x squared. What will the right-hand side be? 1/8, good. We cube the top, we cube the bottom, it's 1/8. Very nice. Now what? Square root, because it says x squared, right? Our goal is to solve for x. So I have x equals. Now, This is one of those places where I'm like, do you remember what happened in the video? And most of you said that you thought you watched it anyway. You raised your hand for me. So when you put a square root on a problem, what do you have to remember to do? You have to remember to put it on both sides. There's something else I was thinking about. I think somebody over here started to say it. You have to put a plus or minus, right? So you need to remember this is something very specific about square roots, fourth roots. It's about the index being even, all right? So when you have a radical that you put in that is an even radical, in this case square root, we have to remember the plus or the minus. And because I have a square root of 1 over 8, that would be the same thing as having the square root of 1 over the square root of 8, right? All right, very good. So now what is the square root of 1? 1. That's a good one. How would I simplify square root of 8? 2 square roots of 2. And if you'll remember, the reason that's the case is because 8 is the same thing as 4 times 2. And the square root of 4 is 2. Okay? So one of the 2's stays under, one of the 2's comes out. Do I get to leave my answer that way? Yeah, that's really like one of those leading questions. Do I get to? And of course you know the answer is no, because otherwise I wouldn't have asked, right? Okay, yeah, so there's a problem. The problem's the radical in the denominator. We don't leave our answers with radicals in the denominators. We need to rationalize them. How do I rationalize a square root 2 in the denominator? The conjugate. And in the case where there's not addition or subtraction, the conjugate looks just like it already does, right? So the conjugate for square root of 2 just is the square root of 2. I don't have to worry about any pluses or minuses. And the 2 that's out in front, it also gets to stay because it's not irrational, right? It's a whole number part. I don't have any problem with it. So I don't need to mess with that part. It's just the square root of 2 that I need to, so to speak, mess with. So I'll multiply by the square root of 2 on the bottom, and if I do that to the bottom, I also have to do that to the top. Okay, good job. So I still have the plus or the minus. On the top, I have square root of 2. What's on the bottom? What's that? It is a 4. So where did the 4 come from? Can you explain for me?
The square root of 2 times square root of 2 is 2, and 2 times 2 is 4.
Right, good. So this 2 right here is going to be multiplied, and then these 2 square root of 2's, when they multiply together, give me the other 2. That makes up my 4. Please don't simplify the 2 underneath the radical and the 4 that's underneath the whole fraction. Those don't simplify because one's underneath a radical and the other one's not. You can't do that, okay? So they are correct just like they're written right now, square root of 2 over 4. Now, a couple of things. When we started this section on roots, I had you write something out to the side that said, like, always check your solutions, absolutely have to, it's not an option kind of thing, right? So it's a true statement, and it's a good statement to do regardless. But on this problem, it's not sort of like absolutely have to, can't possibly move on. What was different about this radical than the last 2 problems? It was a cube root, right? As opposed to a square root. The thing with cube roots and fifth roots and everything else that are odd is that they preserve signs, right? If I multiply something by itself 3 times and it was negative to start with, it's still negative. See, signs disappear when I do it an even number of times, right? And it's the even number of times that makes this absolutely crucial to check these solutions. And it's the fact that this is an odd one that makes it sort of optional of whether I do here. Are you guys with me? Because this is an odd radical, it's not absolutely the most like dire thing in the world to check on this one. It's still a good idea, but if you didn't, it's not going to actually create any of these extraneous solutions. The only thing that could have happened here is if you actually made a mistake in some other fashion, you could catch it, which means it's always a good idea to check your solutions, of course, but you're not going to come up with any sort of arbitrary solutions on a regular basis here, okay? So we're going to move on from this one. Now, we encountered absolute value equations when we did linear equations before. So we've already dealt with some of what I'm going to say today, so it's going to sound like, didn't we already talk about this? And the answer is yes. But there's going to be something new that's going to come up as well that we haven't talked about, okay? Now, the part that we talked about before with absolute values is we talked about the fact that what's under, or not under, but inside of the absolute values could be a positive quantity or it could be a negative quantity. And then when we take the absolute value of it, it always ends up being positive on the output. So the output of this is 1, right? The right-hand side, the final solution of simplifying whatever's inside of the absolute values is a positive number on the outside, okay? But it could be that what's inside of the absolute values is equal to that 1. So it could be that a squared minus 1 equals 1, and then I take the absolute value and I get the 1. Or it could be that what's inside the absolute value is actually a negative 1. And then if I took the absolute value, I would get the positive 1 on the output. Okay, so that's something we've already done before. We talked about that. The part that we haven't done is the fact that at this point, these two equations are not linear anymore, right? When we were dealing with absolute values before, they dissolved into a linear equation that we solved. But now these are absolute values that are actually quadratic. There's a couple of ways to solve quadratic equations. Well, there's, again, like I said earlier, there's lots more than a couple. But at this point on these particular problems, one of them would be factoring like we did before. Obviously, you could use completing the square and all that kind of stuff too. But the other option on this particular one is that we will notice on this equation there's no linear term. There's no a by itself, right? I have an a squared and I have constants, but I don't have a. Are you guys with me? Okay, so when that happens, and when that happened when we did the quadratic section, what you can do is you can make the squared part on one side and then all the constants on the other side and solve from there. It happens to be a little bit faster way of solving a problem. So let's take a look at that for the first one. So the first one, I can add the 1 to both sides. I have a squared on the left and I have a 2 on the right. Okay, so this wouldn't work if I still had an a. But at this point, there's simply one a that I'm solving for because it's only in there one time in the problem. It happens to be squared, but you know how to solve that. How would you get rid of the square? You'd square root. And because you put the square root on, what does that mean? Yeah, you have to take the plus or the minus with it, right? Yeah, that's what you meant to say, right? Yeah, absolutely. Okay, and then we have to still have the square root of 2 on that one. Okay, so that's two solutions, right? Two proposed solutions. Positive square root of 2 and negative square root of 2. All right, we have another half of the problem over here. What happens when I add 1 over here? I get 0. So a squared equals 0. Now what? Square root, same thing. What happens when we square root 0? It's still 0. So there's actually only one solution on that. There's no plus or minus 0. Like 0 doesn't have a sign to it. So we don't have to worry about the plus or the minus here because, you know, it's 0. But there are 3 proposed solutions. Now, I mentioned at the first part of the class that the ones that had square roots, we need to be really, really careful that we checked the solutions. Absolute values are the same thing. We need to be really careful that we check the solutions, okay? Because weird things happen with absolute values, much like weird things happen with square roots that sometimes end up giving us solutions that are not really solutions. So we're going to double check all 3 of these solutions. So we will check a equals 0 first because 0 is a really easy thing to plug into stuff. All right, so if I plug 0 in for a, 0 squared is 0 minus 1 would be negative 1. What's the absolute value of negative 1? 1. So the left-hand side is equal to 1, and that's exactly what the right-hand side is equal. So a equals 0 is a for real solution. Our second one, a equals square root 2. All right, putting it in for a, square root of 2 squared is 2. 2 minus 1 would be 1, and the absolute value of 1 would be 1. So the left-hand side's 1, the right-hand side's 1. Square root of 2 is a for real solution as well. That one works. And now we're going to try the negative square root of 2. Write that very well. There we go. All right, so negative square root of 2 squared is negative 2 or positive 2? It's positive 2. Remember, when we square negatives, the negative disappears. So this still gives me a 2, just like the square root of 2 did. 2 minus 1 is 1, and then the absolute value of 1 is 1. So on this one, all the solutions actually did work. So every proposed solution was a for real solution. So we have, hang on, 3 solutions on this particular problem. All right, this one looks a little bit different because why? Yeah, there's absolute value on both sides, right? Okay. So what are we going to do when there's an absolute value on both sides? Well, much like the last problem, there will be two possibilities. Now, one possibility is that both of these absolute values are exactly equal to the same thing already without the absolute value. Like, for instance, if the left-hand side equals 5, the right-hand side also equals 5, the absolute values just don't even matter, right? Like, that's a possibility. So one possibility is that we simply could remove the absolute values because they really didn't matter. Both values were the same. Or perhaps both values were negative. Negative, square root of 5, or not square root, excuse me. Negative absolute value of 5 and absolute, I didn't say that right because I said it backwards. Absolute value of negative 5 on the left, absolute value of negative 5 on the right, so they're both negative, right? That's also possible. So this one was 2x plus, 7. Okay, so one possibility is the absolute values just really they're not necessary. The other possibility is that, say, for instance, one side is negative 5 and the other side's positive 5, right? So that when I take the absolute value, they're the same, yeah? Okay, so the second possibility is that they're the same except that there's different signs. So one of them is 2x minus 3. The other one would be the opposite value. So we'll put a negative 2x plus 7. Notice we only put it on one side because putting it on both sides would make it just like the first equation I already wrote down. It wouldn't change anything. So there really are only two options. They're identical already, or they're negatives of each other. So these are our two options, and we're going to solve both equations and see where that leaves us. Now notice what happens on the first equation. What happens when we start to regroup the x's? They go away, right? I do minus 2x on both sides, and before I know it, I've got negative 3 equals 7, and we're like, no, that doesn't work, right? So what does that mean? Well, it simply means that this is not possible. They aren't equal to each other without the absolute values. There's no solution that comes from that. On the other one, I'm going to distribute the negative through. So I have negative 2x minus 7. I'm kind of a fan of making x's positive, so I'm going to add my 2x on both sides if you guys are good with that. So I have 4x minus 3 equals negative 7. What would I do next? Add the 3. So 4x equals what? Negative 4. And then divide by 4, right? So what does x equal, at least potentially? Negative 1. And we want to check to make sure that that's true. Okay. So if I plug negative 1 into the equation, 2 times negative 1 would be negative 2. Negative 2 minus 3 would be negative 2 minus 3 would be negative 5. And then the absolute value of negative 5 would be 5. So now I'm kind of cheating, but this really did happen by accident. I was just randomly using 5s in my first class, and then all of a sudden when we got to 5 here, it was kind of funny because like I just was making up a 5 along the way. So it actually equaled negative 5. We took the absolute value. We actually got a 5. That's it's not coincidence this time because it happened 2 hours ago. But it's not always going to be 5s, okay? Maybe it's 7s or 5/3 or something next time you do the problem, a different problem. Right-hand side, 2 times negative 1 would be negative 2. Negative 2 plus 7 would be 5, and then the absolute value of 5 is 5. So on this one, these actually do have a solution. It is the solution value of x equal negative 1. Okay, so be careful. 5s kept, blowing around in the wind through that entire problem, and 5 had nothing to do with what the answer is, right? It's just what both sides are equal when I plug the number in. So x equal negative 1 is actually my solution. All right, one more type of problem that we're going to look at. Okay, so we've done roots, we've done absolute values, and then the third type in this section is quadratic type. Okay, so write this one down, and the first thing I want you to think about, don't say it out loud, give everybody just a chance to think. I want you to think to yourself, why is this not a quadratic? Don't say anything yet. Okay, why is this not a quadratic? There's an x to the fourth. That's exactly right. Quadratic means we have x squareds, we have x's, and we have constant terms. And this one has an x to the fourth. So everybody understands that part first, right? Now, let's say for an instance, this problem, other than that, it kind of looks like the same pattern, right? It almost looks like you've got, a trinomial with an x squared in it. It kind of feels like it should be similar, and it is similar. What if the problem instead had said x squared minus 7x plus 10? So instead of the power 4, we had a power 2, and instead of in the middle power 2, we had a power 1. What would we do in this problem if it looked like that? We'd factor it, right? Okay, so how would it factor? Well, there'd be x here and x here.
X minus 2x minus 5.
Okay, so negative 2 and negative 5. That would give me a positive 10 at the end, right? And it would give me a negative 7 in the middle. Is everybody good with that? Okay, so the reason these two, the examples that we're going to do, are considered a quadratic type is because they're solved in the same way. We can factor them much like we would have with a quadratic. Instead of having an x squared, or an x, excuse me, we will have an x squared here because x squared times x squared is x to the fourth. And we'll actually do the same thing on the next pieces. I need two numbers that multiply to 10 and add to negative 7, and it's a negative 2 and it's a negative 5. It's the same process, okay? And then, what would the next step be if I were doing the quadratic over here? Solve how? Like, what would be physically, what would I write down?
X squared minus 2 equals 0.
Okay, so we're going to set each piece equal to 0, right? So we're going to write down x squared minus 2 equals 0, and we're going to write down x squared minus 5 equals 0. And because, again, there's only a single x in each one of them, we can actually, move the number over and solve from here. We can isolate the x. So if I add my 2 to both sides, this tells me then that x squared equals 2, and this is x squared equal 5. And then what would I have to do next? Square root, exactly. So we would square root both sides, and because we put the square root on,
Plus or minus.
yes, we're going to do a plus or a minus on each one of those. And so how many solutions do I actually end up getting? I end up getting 4 solutions. Now, again, is it a good idea to check your solutions? Well, of course it is. But there's nothing in this process that's going to arbitrarily come up with extra solutions like they did in the radical one or in the absolute value one. So I leave it up to you whether or not you want to check yourself at this point, because weird things don't happen through the process like they did on the other ones, okay? Okay, I have one more example. You ready? I never looked at the clock and said, how much longer do we have? We have enough, I'm sure. Write all the details in, and I promise it's not as scary as it looks. Okay, so I haven't examined all of your hands super carefully, but I think you all have 2 thumbs. Does everybody have 2 thumbs? Okay, I want you to take your 2 thumbs and I want you to cover up the part right here. I'm going to call mine blobs, and right here. Cover them up on your piece of paper, okay? If the pieces that you have covered up simply said x, then you would have x squared minus 2x minus 3, right? And it would look like a quadratic. Agreed? Okay. That's exactly why this is a quadratic type equation, is because it has that same basic form, that those blobs, when they're covered up, are acting just like x would act in our problem. So in some sense, if I were to write this out, I could write, and I'll go back and I'll make it look better in a minute here, blob, and blob right here. Okay, I could make those sort of the X location. We'll fill them in a minute. And the rest I would process the same way. At the end, this says -3. In the middle, it says -2. I need two numbers that multiply to give me -3 and add to give me -2. What would those be?
-2 and -1.
Right, so we're going to need, not -2, -1. You're close, though. -3 and +1, yeah. So I would need -3 and +1. Those multiply to -3 and add to -2, right? And the part where I put my thumbs, or in my case on the screen up here, where I put the yellowish blobs, will say the same thing that the original yellow, the one was covered up now. There. They will say u squared plus 2u. So where I have my blobs, I'm going to rewrite now u squared plus 2u. It's just a replacement issue. Cover them up with your hands. Label them a different letter if it helps. Whatever it helps you to see it. It's really just a quadratic in disguise. Okay? Now, there is something that's different at this point. You notice, what is this particular piece in and of itself? It actually is a quadratic. Not only is it a quadratic, but it's a quadratic that factors. So we're going to take that piece and we're going to factor that piece. Well, it says u squared, so that's u and u. I need two numbers that multiply to -3. I feel like we've done this before. But now they have to add to 2. What are those numbers? Now it's +3 and -1. Multiply to -3 and they add to 2. But lo and behold, on this one, it happens to be true that this piece over here is also a quadratic, and it also factors. Now, at this point, if it didn't factor, you could use the quadratic equation, or maybe the quadratic equation gives you some eyes, you know, something like that, so it's non-real and you're only looking for real solutions. Maybe it doesn't give you anything extra. All those are possibilities, but this one, it doesn't. It just factors, okay? So as we look at this one and we attempt to factor this, how will this one factor? Yeah, I've got a u and then +1 and a u with another +1. It's a very straightforward one. Oh, and I left off my =0. Don't you guys do that. Leaving things off as a bad plan. Put =0. That still equals 0 at the right-hand side. Okay, they're all linear now. Now what do I do with them? Yeah, I'll set each of them up as their own equation. You bet. So x plus 3 equals 0. Not x, u. U minus 1 equals 0. U plus 1 equals 0. And it happens to be that two of these match. That's fine. It just means I'll have one fewer solution when I'm done. What values will u equal from each of these pieces? -3, 1, and -1, and there's another -1, but I'm not going to write it because it's the same as the one before. Don't need to necessarily. I have 3 potential solutions, just like on the other one that I mentioned earlier to this one. I didn't do any square rooting and I didn't have any absolute values. So I'm not going to check them with u. It's still not a bad idea to check it, right? Checking your solutions is never going to be a bad idea. All right, it could also catch any other kind of mistakes, but there aren't going to be any inherent mistakes that come along the way that the other two had.